In the last lecture, we have seen the modeling of DC machine. In that case, the armature and the field currents both are DC currents. Now, today in this lecture, we will take up the modeling of an induction machine, which is an AC machine, and it is a 3-phase symmetrical induction machine. So, we will discuss the modeling of a 3-phase symmetrical induction machine. Modeling of 3-phase symmetrical induction machine. Now, a 3-phase machine will have 3 phase in the stator and 3 phase in the rotor. In an induction machine, the rotor is very often squirrel cage. It means the rotor does not have any windings, but have symmetrical bars distributed over the surface of the rotor, embedded inside the rotor and sorted by means of end rings. However, that is also symmetrical because the bars do not have any, are symmetrical, they do not have any fault. Each bar is of the same length, same thickness. So, we can consider the rotor to be also symmetrical. So, let us try to draw this. So, we have a rotor here and we have 3-phase stator. This is phase A and we excite this from a voltage source, that is VAS, this is phase B shown in yellow color, and we excite this from a voltage VBS and we have a phase C shown in the blue color, and we excite it from a voltage source, that is VCS. And the rotor also has 3 windings. We can similarly show the rotor windings as AR and then BR and then CR. And the rotor is rotating in the anti-clockwise direction at a speed of omega r. The phase sequence here, we can assume that the phase sequence is ABC and there is a revolving field from A to B to C. The rotor tries to rotate in the same direction as that of the revolving field. So, it is rotating in the anti-clockwise direction as shown in this particular figure, and the rotor is short circuited. So, we can show that these 3 windings are shorted. Okay. So, when we want to model this induction machine, we have got 2 ways out. What are the 2 different methods? The first one is the modeling in actual variables. Now, what are the actual variables? The actual variables here are the voltages and the currents. Here in phase A we have got VAS, similarly we have got IAS here, phase A current. In the phase B we will similarly have IBS, and in phase C we will have similarly ICS. So, we have 3 currents in the stator and similarly we will have 3 currents in the rotor as well. So we have here IAR, here IBR, and here we have ICR. As per the Cron's primitive machine model, we assume that the terminal closer to the center is positive. So you can see that in this winding, this terminal is close to the center compared to the other terminal. So we have assumed that this is a positive terminal. Similarly for the rotor, so the currents are entering the positive terminals of the winding, that as per the convention of the Cron's primitive machine model. And here we can simulate the machine in the various variables. So we have IAS, IBS and ICS. For the stator we have 3 currents, and similarly we have IAR, IBR and ICR for the rotor. So we have 3 currents for the stator and 3 currents for the rotor. So we have to essentially solve for 6 variables, 6 currents, and we have the forcing functions are VAS, VBS and VCS. For the stator, and for the rotor we have correspondingly the voltages VAR, VBR and VCR, and for a normal induction machine VAR, VBR and VCR are supposed to be 0 because the windings are short circuited. So these are 0 voltages. So we can simulate an induction machine in actual variables, and the actual variables are IAS, IBS, ICS, IAR, IBR and ICR, and the forcing functions are VAS, VBS and VCS, VAR, VBR and VCR. So the second way, as you know that we have 6 variables here, so the simulation is going to be complex. It is not going to be an easy one. But if we transform these variables into DQ model as similar to a Cron's primitive machine model, the number of variables can be reduced, and there are some other advantages also, that the inductances will be constant. The inductances will be independent of the position of the rotor. So that is the second advantage. And if we simulate an induction machine in DQ variables, the simulation will be simpler than that of the actual variable simulation. So modeling in actual variables, that is in ABC variables, and the second one is modeling in DQ variables. So we will take up the first one first, number 1, and try to understand how we can simulate an induction machine in actual variables. So we can write down the equations VABCS. This is basically a vector, and this has got 3 components, that is VAS, VBS and VCS. This is a vector, and we can write down the equation for the phase A, equation for phase B and equation for phase C. All right. So we can say that this is equal to RS. It is a symmetrical machine. So by symmetrical machine we mean the phases are balanced. So each phase has a resistance of RS. So we will naturally have a resistance drop, that is RS into IABCS plus the rate of change of flux linkage. So we can say here P psi ABCS. So psi ABCS is again a vector having 3 components, 3 elements here: psi AS, flux linkage in phase A stator; psi BS, flux linkage in phase B stator; psi CS, flux linkage in phase C stator. And similarly we can write down the equation for the rotor. VABCR, that is VAR, VBR and VCR, and that is equal to RR. The rotor is also symmetrical, IABCR plus P psi ABCR. And here we have already seen that ABCS has got 3 components, IAS, IBS, ICS, and psi ABCS is also a vector which has got 3 components, psi AS, psi BS, and psi CS, and psi ABCR, the rotor flux linkage, is also a vector which has got 3 components or 3 elements, the phase A flux linkage, phase B flux linkage, and phase C flux linkage. So, this is the equation for rotor, and stator and the rotor equations will be 6 equations, 3 equations for the stator and 3 equations for the rotor, and we have to solve these equations and find out the values of the currents of the stator, IAS, IBS, ICS, and the rotor currents similarly IABCR, that is IAR, IBR, and ICR. So, we can solve this equation. These are the differential equations. We can solve the simultaneous 6 differential equations to find out the values of the currents, the stator currents IAS, IBS, ICS, and the rotor currents IAR, IBR, and ICR. And after we find out the currents, we can find out the torque, because torque is a function of the currents. And from the torque we can find out the speed. Now, with this introduction, let us try to see what is this psi ABCS and what is this psi ABCR. We will first take up psi ABCS and see what is psi ABCS. Now, if you see, psi ABCS is the total stator flux linkage. It is basically a vector having 3 elements, and we know that the stator and the rotors are coupled together. It is not that we are only having stator, not having rotor. Both are present and both are magnetically coupled. So, the flux linkage in the stator will be the flux linkage due to its own current and also the flux linkage due to the rotor current. So, we can understand that the flux linkage in the stator will have 2 components, and the 2 components are as follows. We can say that it is psi ABCS is the flux linkage in the stator due to its own current plus the flux linkage in the stator due to the rotor current. Similarly, in case of rotor also, psi ABCR, the flux linkage in the rotor due to the stator current plus flux linkage in the rotor due to the rotor currents. So, the rotor will also have 2 components of the flux linkage due to its own current and flux linkage due to the stator current. Now, we can see that if you see this particular term psi ABCS, the flux linkage of the stator due to its own current. It means whenever the currents are flowing in the stator windings are producing some flux, and the flux is also linking the stator windings. Now, if we express this in terms of inductance, because ultimately when a machine is available to us, we do not know the flux linkage directly, we know the machine parameters, and inductance are important parameters of the machine. So, the inductances are given or known. So, the inductances are specified, and we will find out what is this inductance matrix. So, this inductance matrix will have LAA, and we have here LAAS, LABS, LACS. This LAAS, it means the inductance of the stator phase A with respect to the phase A. Inductance of stator phase A with respect to phase B is LABS. Inductance of stator phase A with respect to stator phase C is LACS. Similarly, we can have BAS, BBS and BCS, and also LCAS, LCBS and LCCS. So we can call this to be matrix LSS. It means something like a self inductance of the stator. The flux linkage in the stator due to its own current. So we can say that capital LSS is the self inductance of the stator. All right. So similarly, we can say psi ABC is due to the rotor currents, this component, that also will be written in terms of inductance and current, but instead of stator we have the rotor currents producing the flux linkage, IAR, IBR and ICR. And here we will have ASAR, ASBR, ASCR, BSAR, BSBR, BSCR, CSAR, CSBR, CSCR. So this actually is a matrix which is something like a mutual inductance between the stator and the rotor, and we call this matrix to be capital LSR. So this matrix is LSR, which is the mutual inductance between the stator and the rotor. So let us try to evaluate what is the various inductances here. All right. So we can evaluate the inductances. And number one, we will find out the stator self inductance. Now, what are the stator self inductances? The stator self inductances are LAAS, LBBS and LCCS. Now, if you go a little back, we are trying to find out these inductances. This inductance, this inductance and this inductance. Okay. This is basically inductance of phase A with respect to itself, inductance of phase B with respect to itself, inductance of phase C with respect to itself. So this is not very difficult to find out, because we know that the self inductance will have two components. One component is contributed by the leakage flux, that is the leakage inductance, and the other component is the magnetizing inductance. So we can write this in the following fashion: LLS plus LMS. LLS is the leakage flux or the leakage inductance, LMS is the magnetizing inductance of phase A. Similarly, phase B, LLS plus LMS, the phases are symmetrical, so the inductances will be the same, LLS plus LMS. Now, when we talk about LMS, LMS can be represented in terms of the number of turns of the stator and also the reluctance of the magnetizing path. So we can say that LMS can be given as Ns square by reluctance of the magnetizing path. Ns square is the effective number of turns of the stator. The stator is a distributed winding, and of course whenever it is distributed, we always have the pitch factor and the winding factor. Pitch factor So, if you find out the effective number of turns, Ns is the effective number of turns which has taken into account the pitch factor and the distribution factor. So, if you multiply the actual number of turns by the pitch factor and the distribution factor, what you obtain is Ns, that is effective number of turns. And Rm is the reluctance of the magnetizing path, or we can also write down in terms of permeance. So, Ns square into Pm, Pm is the permeance of the magnetizing path. So, this will be same for phase A, phase B, phase C, and hence we can say that the inductances, the self inductances are equal. Now, we can find out the second is the stator mutual inductance. Now, what are the stator mutual inductances? Now, they are L, A, B, S. Now, let us just go back to our earlier thing. Now, the inductance between phase A stator and phase B stator, that is the mutual inductance between phase A and phase B stator. Similarly, the inductance between phase B and phase C stator is BCS, or the inductance between B and C of the stator. The inductance between C and A will be LCAS. Now, they are all equal because the machine is a symmetrical machine and the windings are phase shifted by 120 and 240 respectively. We can always say that the mutual inductance between the two phases of the stator will be the same. So, we can find out this L ABC ABS equal to L BAS, AB and BA will be the same, that is equal to LBCS, LCBS equal to LCAS, LACS. Now, what is this? Now, that is equal to, since the flux is distributed sinusoidally, we can see that the component of the flux produced by phase A linking phase B will be by a factor of cos 120. So, we can say that this is LMS into cos of 120, because this angle is 120, angle between phase A and phase B is 120, and hence we can say it is LMS cos of 120, and that is equal to minus of half LMS. So, we can write down the matrix LSS. Now, we can write down this matrix LSS. So, psi ABCS due to its own current, that is equal to, this is LLS plus LMS minus half LMS minus half LMS minus half LMS LLS plus LMS, and here also minus half LMS minus half LMS and LLS plus LMS. So, this matrix is LSS. We have been able to find out this multiplied by IAS, IBS and ICS will give me the stator flux due to its own current. So, psi ABCS of S equal to LSS into IAS, IBS, ICS. So, LSS has been found out. Similarly, we can find out the mutual inductance between the stator and the rotor. So, we can say that the third one is the mutual inductance between the stator and rotor. Now, what is this mutual inductance between stator and the rotor? Let us go back to our original slide. Now, if you see here, the rotor, this is the rotor axis, rotor phase A is AR and stator phase A is AS. This is the stator phase A axis. So stator is stationary, rotor is moving away at the speed of omega r, and thereby the angle is increasing. So this angle between the stator and the rotor, this angle is theta r. Theta r is constantly changing, and that is why the mutual inductance between AR and AS will be changing, will be a function of theta r. So we can find out this. If you want to find out the inductance between AR and AS, that will be a component of cos theta r. Okay. So we can just say that L AS AR, that's equal to L BS BR. Let's see here. Now the situation between AS and AR will be same as the situation between BS and BR, and the same thing will be happening between CS and CR. So we can say that this inductances will be equal. AS AR equal to L BS BR equal to L CS CR. Now what is this inductance? This inductance is LMS into cos theta r, because the angle between AR and AS is theta r. So it is cos of theta r into LMS. But LMS is the magnetizing inductance, but we are talking about the mutual inductance. So magnetizing inductance is basically referred from the primary side. Now if you talk about the mutual inductance will take into account the number of turns of the rotor and that of the stator also. So in this case we can multiply here by NR by NS. NR is the effective per phase number of turns of the rotor, NS is the effective per phase number of turns of the stator. And in a similar way we can calculate LAS BR, which will be same as LBS CR, LCS AR, and that will be equal to NR by NS into LMS cos of theta r plus 2 pi by 3. We are talking about the interaction of AS and BR, AS here and BR here. Now this angle between AS and BR is 120 plus theta r, 2 pi by 3 plus theta r. That's what has been shown here. All right, cos of theta r plus 2 pi by 3. Similarly, we can have LAS CR, that's equal to LBS AR, that's equal to LCS BR. Since it is symmetrical, we can write without any difficulty NR by NS into LMS cos of theta r minus 2 pi by 3. So this is about the stator. Now similarly we can write down for the rotor. Now what about the rotor? Now if you see the rotor equations are given here. This is basically the rotor equation. So we can have similarly in the rotor the flux linkage due to its own current and the flux linkage due to the stator current psi ABCR of S. So we can write down the rotor equation. We can say here that psi ABCR of S, this for the rotor flux, rotor flux linkages. So psi ABCR of S is the flux linkage in the rotor due to the stator current. Now this is basically a matrix plus psi ABC R of R, the flux linkage in the rotor due to its own current. This is the total rotor flux linkage ABC R. So these are all vectors. So we can write down the component of fluxes ABCR of S, that's equal to I have here the currents IAR, IBR, and ICR, and here I have AR AS, AR PS, AR CS, and BR AS, BR BS, BR CS, CR AS, CR BS, CR CS. In a similar way, we can, this is called the mutual inductance between the rotor and the stator, LRS. Now, in a similar way, we can find out ABCR due to its own current, there is small change here. These will be the stator currents, IAS, IBS, and ICS. Now, these will be the rotor currents, IAR, IBR, and ICR, and this matrix will be AAR, ABR, ACR, LBAR, BBR, BCR, LCAR, CBR, CCR. Now, this matrix is a self inductance of the rotor. So, we can call this matrix to be, as we have LSS, we can call this to be LRR, the inductance of rotor with respect to itself. Now, we can evaluate this LRR and also LRS as we have done in case of the stator. Similarly, we can evaluate this inductance for the rotor. So, we can say that first of all the rotor self inductance out of symmetry, we can say LAAR is equal to LBBR is equal to LCCR. The rotor is also a symmetrical rotor. So, we can say that the inductance of each phase of the rotor will be the same. So, LAAR is equal to LBBR is equal to LCCR, that is equal to the leakage inductance LLR plus LMR. LLR is the leakage inductance per phase leakage inductance of the rotor, and LMR is the magnetizing inductance of the rotor. And there is a relationship between LMR and LMS. LMR is the magnetizing inductance of the rotor seen from the rotor side. So, that is equal to NR by NS square into the magnetizing inductance of the stator seen from the stator side, because the rotor and the stator share the common magnetic path. There is a air gap which is coming in between, and the rotor and the stator will have the common magnetic flux, and since they have the common magnetic flux, depending upon from which side you see, the number of turns will be multiplied. So, if you see from the rotor side, it will be LMR, which is NR by NS square into LMS. If you see the same thing from the stator side, it will be LMS, and LMS has a component of the stator number of turns, that is NS square. Okay. We can evaluate similarly the rotor mutual inductance. Now, LABR is equal to LBAR is equal to LBCR is equal to LCBR is equal to LCAR is equal to LACR. Now, since the rotor is also symmetrical, we can write down this equation, and this is equal to LMR into cos of 120, because we know that in the rotor also phase A and phase B are shifted by 120 degree. So, if we want to find out the mutual inductance between AR and BR, it will be LMR into cos of 120, because AR and BR has an angle of 120. The axis of AR and axis of BR are spread apart by an angle of 120. So, that is why we can say that LMR into cos of 120 is equal to LABR, and that is equal to minus of half LMR. So, this is what we have found out, and then we can find out the mutual between the rotor and the stator. So, that we can see here psi ABCR of S. Now, this if you write down in this case, this will be, if you fill up this particular matrix, that will be the mutual between the stator and the rotor. So, this matrix will have the following expression: cos theta r minus of 2 pi by 3 cos theta r plus 2 pi by 3 cos theta r plus 2 pi by 3 cos theta r minus 2 pi by 3 cos theta r minus 2 pi by 3 cos theta r plus 2 pi by 3 cos theta r. This is multiplied by IAS, IBS and ICS. Now, we are writing down this component of the flux. So, this flux is linking the rotor due to the stator current. So, this involves the mutual inductance between the stator and the rotor, and the mutual inductance is expressed in the following fashion. This is the mutual inductance between the stator and the rotor. So, we have LMS here, NR by NS into cos of theta r, cos of theta r minus 2 pi by 3, cos of theta r plus 2 pi by 3. So, this is the mutual inductance. So, we can say this is to be RS. The mutual between the rotor and the stator is LRS. Now, it is interesting to note that LRS is equal to the transpose of LSR. This can be verified, that if you transpose this matrix, what you obtain here is that it will be LSR. Of course, there will be some number of turns factor will be there, but this will be LRS equal to LSR transpose into NS by NR. This number of turns will be multiplied, but the main matrix which is containing cos theta r minus 2 pi by 3 cos theta r plus 2 pi by 3, the transpose of that will be appearing in LSR. Okay. So, this is what we can see here. Okay, we can just go back and see, this is LRS. LRS is given by this, and this multiplied by NS by NR will be the transpose of LSR. Okay. So, these actually are the equations in the actual machine variables, IAS, IBS, ICS, IAR, IBR, ICR. But very often whenever we have a machine, we would like to refer everything to the primary side, that means to the stator side. All the parameters that we have in an equivalent circuit are also referred from the primary side. So, there is a need to transform all these variables to the primary side, which is the stator. So, we can see that transformation to the stator side. So we know we have the equation here, VABCR is equal to RR IABCR plus P psi IBCR. Now we can transform this equation to the stator side. Now how do we transform? We can transform this by multiplying suitable ratio of number of turns. So we can multiply the left hand side with Ns by Nr. Ns by Nr into VABCR, that's equal to Ns by Nr square RR. Nr by Ns, we have some mathematical manipulation here, IABCR, and this the flux we can write as P of Ns by Nr into psi ABCR. This we can write, and we can further simplify this in the following fashion: Ns by Nr into V ABCR, that's equal to Ns by Nr square RR Nr by Ns IABCR plus we can expand this Ns by Nr whole square LRR Nr by Ns into IABCR plus Ns by Nr into LRS I ABCS. So this is basically the equation after transformation. Now what we have done is that we have transformed to the stator side by suitably multiplying the number of turns. Okay. So the left hand side would be IABCR prime, the rotor voltages as referred to the stator side, IABCR prime, and then in the right hand side we have Ns square by Nr RR. So that is basically RR prime, the rotor resistance referred from the stator side, and then Nr by Ns into IABCR, that is IABCR prime, the rotor currents referred from the stator side, plus we have this P term, the derivative term, and within that we have LRR into Ns by Nr whole square. Now that is actually LRR prime, the rotor self inductance referred from the stator side. So we can write that as LRR prime, alright, and then we have Nr by Ns into IABCR. So that is actually IABCR prime, the rotor current referred from the stator side, plus LRS into Ns by Nr. So that is LRS prime, the mutual inductance between the rotor and the stator referred from the stator side, into IABCS. So this is a transform equation. So by multiplying the ratio of the number of turns, we have transformed this to the stator side. Alright. Now similarly in the stator equation, we have got VABCS, that's equal to RS IABCS plus P psi ABCS, and that's equal to RS IABCS plus P. We can express the flux in terms of the inductance and current. So we can say here that is LSS into IABCS ABCS plus LSR, the mutual between the stator and the rotor, IABCR. And here we can do some manipulation in this case, because in the stator equation we do not have to do much transformation, because stator is already transformed to the stator side. So, we have to just transform that part which involves the rotor current. So, this is shown in ordinary line term. So, this we have to transform, and to transform that we can do some mathematical manipulation. Plus P LSS IABCS plus we would pre-multiply this with NS by NR, and then we have LSR here, and then post multiply with NR by NS into IABCR. Now, NR by NS into IABCR is IABCR prime. So, we can rewrite this in the final form, that is RS IABCS plus P LSS IABCS plus LSR prime into IABCR prime. So, this equation that we have obtained finally is basically the transform equation seen from the stator side. So, we have been able to derive the equation for the various currents IAS, IBS, ICS, and IAR, IBR, ICR refer to the stator side. Okay. Now, let us see how we can find out the expression for the torque. Torque equation in machine variables means ABC variables. So, we are interested to find out the expression for the torque or the equation for the torque in ABC variables. Now, how is the torque produced? We have actually coupling field between the stator and the rotor, and any change of the field will result into the mechanical output. So, what we have here, we have an electrical system and we have a mechanical system. And these systems are connected by means of a magnetic field. The rotating machine converts the electrical energy into mechanical energy, or mechanical energy into electrical energy, depending upon whether it is a motor or a generator. Now, the field between the stator and the rotor is a coupling field, and the coupling field is basically the mutual field or the magnetizing field which does not have any component of the leakage flux. So, we can write down the expression for the coupling field. Now, if you have two coils like this, one coil like this and the second coil like this, and these two coils have the self inductance as L1 and L2 respectively, and these two are magnetically coupled, all right, and there is a mutual inductance between these two which is M, and the current flowing in the primary is maybe I1 and current flowing in the secondary is I2 as shown in the figure. And if you want to find out the magnetic field, in this case the stored energy in the field, the stored energy is basically given by Wf is L1 half L1 I1 square plus m I1 I2 plus half L2 I2 square. Now, if you are finding out the stored energy in the coupling field, the coupling field is the field that couples the primary with the secondary. Now, that field does not have any leakage component. These are the leakage fluxes. The leakage fluxes do not link the coupling field. Now, this field will not have any leakage flux or component. So, if I want to find out, let us say, the field, coupling field, that will be half of L1 minus L1. Small L1 is the leakage inductance into I1 square plus the mutual inductance I1 I2 plus half L2 minus. So, the coupling field is given by half of capital L1 minus small L1 into I1 square plus m I1 I2 plus half of capital L2 minus small L2 into I2 square. The small L2 is a leakage inductance of the second coil. So, the coupling field does not involve any leakage flux, and hence the inductance are suitably modified by subtracting the leakage inductance from the self inductance. So, similarly, if you have the expression for the coupling field in an induction machine, we can write down in the following fashion: Wf is equal to half of IABCS transpose LLS minus LLSI IABCS. This is the self inductance plus IABCS LSR referred from the primary side, IABCR, because we are referring all variables now from the primary side. So, we have this prime means the variable is referred from the primary side, plus half IABCR transpose LRR prime minus LLR prime I is the identity matrix into IABCR prime. So, this is basically the field stored in the coupling field, or the energy stored in the coupling field. And since we are assuming a linear magnetic circuit, we have assumed in the very beginning that the magnetic saturation is neglected. So, which means that this energy stored in the coupling field is same as the co-energy. The energy is equal to the co-energy for a linear magnetic circuit. So, we can say that is also equal to the co-energy Wc. And from this co-energy we can find out the expression for the torque. So, we can say that the mechanical output, this is the work done, is equal to minus Te into d theta m, and this is basically the work done in this case. And if you want to find out Pe can be calculated as the pole pair into the derivative of the co-energy with respect to theta r at constant current. We can say that current remain constant at constant current. So, all currents of the stator and the rotor will be kept constant. So, if you take this co-energy and differentiate that with respect to theta r multiplied by P by 2, that will be the torque expression. Now, why this P by 2 is coming into picture? Because this is Te into mechanical thing. So, that is equal to Te into d theta r by P by 2. And hence, if you want to find out theta r, you have to take this P by to the other side. So, we can say here that the torque is equal to the derivative of the energy with respect to d theta m, negative of that at constant flux linkage, or that is equal to the derivative of the co-energy with respect to theta m at constant current. So, because it is the derivative of the co-energy with respect to theta m, that is why we have a positive sign here. So, we have a plus sign here, and this is p by 2, because we are talking about the electrical angle. Theta e is the electrical angle, theta e is equal to p by 2 into theta mechanical, that is the mechanical angle. So, this is the expression for the torque, and if we see this co-energy is same as the energy, because we are talking about a linear magnetic system. So, out of these three terms that we have here, this is one term concerning the stator, this is the rotor, and this is the mutual. So, in this case, this will be independent of theta r, this will only be a function of theta r. So, we have to differentiate this with respect to theta r to find out the torque. So, finally, you can see that the torque can be obtained by differentiating this part with respect to theta r, and the part is IABCS LSR IABCR, and since LSR is a function of theta r, when you differentiate this with respect to theta r, you get the torque, that is Te. Now, you know that this LSR will be a function of cos theta r minus 120, cos theta r plus 120. So, we can differentiate that and then simplify this. That expression will be a complex expression. We can finally write this expression as follows. That is equal to minus p by 2 LMS IAS IAR prime minus half IBR prime minus half ICR prime plus IBS into IBR prime minus half ICR prime minus half IAR prime plus ICS into ICR prime minus half IBR prime minus half IBR prime. This is ICR prime minus half IAR prime and then minus half IBR prime multiplied by sine of theta r plus root 3 by 2 into IAS into IBR prime minus ICR prime plus IBS into ICR prime minus IAR prime plus ICS into IAR prime minus IBR prime into cos of theta r. So, this is the expression for the torque, and in this particular lecture we have simulated, modeled the induction machine in ABC variables. In the next lecture we will see how we can transform this ABC variable into DQ variables.